We start today our lecture on business intelligence. Today is May 15. We are going to look at dynamic systems today. Okay, so the dynamic of one and two-dimensional systems. Okay, we are going to focus on two examples. Okay, I tried to make them interesting for you, so I took a topic that maybe makes it interesting. You can do the transposition to business dynamics. Okay, actually it's the same mathematics behind, but with other examples. So we're going to look at the one-dimensional example with the transmission of sexual disease. We're going to take the example of chlamydia in a population of students. So imagine we have n students, okay? And at the time point t, the number of infected students is given by the function e big I of t, okay? So we can describe a function I big of t as a function of t, so the number of infected students, okay? Because the population is constant, n individuals, we can normalize I of t between 0 and 1. We do so by dividing I of I big between n. Okay, so if we say I of t equals I of t small equals I of t divided by n, this belongs to the interval 0 and 1, because the maximum number of or the maximum value of I of t big is n, that we can have only n students infected. So we haven't lost any generality, but now our function is bounded to 1. Okay? So we want to know the dynamics of we would like to understand the dynamics of I of t. For this, we define two processes. Process number one, infection. Okay, so every infected person, individual, can infect other individuals with rate beta. Okay, so every infected person in average does infect other healthy individuals with a speed of beta. Okay, so the frequency that an infected individual meets a healthy one is I times 1 minus I. So the infection rate is given by beta times I times 1 minus I. Okay. That's the infection rate. Good. Then there's other process of curation. Every infected person can get cured. Okay. With rate gamma. As a result, the curation rate equals gamma times I. Okay. If you wish, beta is the number of times infected people make out with without protection with not infected people, with healthy people, and gamma is the rate of curation. So you get a treatment from the doctor, some pill or some cream, and then chlamydia just disappears. Okay. So the dynamic system describes I as a function of t when time changes. Okay, so the change of I as a function of t, okay, is going to equal the infection rate minus the curation rate, right? So the first derivative of I divided by time, or as a function of time, is beta times E times 1 minus E minus gamma times E. As a result, we have beta times E minus beta times I squared minus gamma times E. So we can put that together, and now we solve the equation beta minus gamma times E minus beta times E squared. Okay? So we want to solve this equation. We define two parameters, R, beta minus gamma. Okay, so this is the infection rate minus curation rate. And we say that K equal R divided by beta, which equals beta minus gamma divided by beta, which equals 1 minus gamma divided by beta. This is equal to say that beta equals R divided by K, by the way. This is just a definition, okay? So we know that this trick helps us, and these parameters have a physical interpretation. R is the difference between the rate of infection minus the rate of curation. If R is bigger than 0, then we infect faster than we cure. So the infection is going to spread. If R is smaller than 0, the infection is going to disappear. If R is equal 0, we have an equilibrium. And yeah, so we put this together, these two parameters in the equation above. And as a result, we have that the first derivative of I equals R times I minus R divided by K I squared. Okay, so we can say that R times I multiplies 1 minus I divided by K. And this is what we call the logistic equation. The logistic equation. So in order to solve this, we need to know two things from calculus. I will make here a tiny reminder. Okay. So a tiny reminder. The first thing is that the derivative of the logarithmus of x is to x is equals 1 divided by x. As a result, the integral of 1 divided by x equals the logarithmus of x plus a constant. Okay, that is the first one. The second thing to know here is that k divided by x1 minus x. We need to separate this, and for this we are going to make a little trick. Two parameters, a and b. Okay, so a1 minus x plus bx divided by x1 minus x. So if x equals 0, then k equals a times 1 minus 0 plus b times 0. So k equals a. If x equals 1, then k equals a times 1 minus 1 plus b times 1. So k equals b. Okay. So if we take our equation, the logistic equation above, we can write it this way. Ri 1 minus I divided by k equal dt, or I put the r above better, r dt. Okay. So we can of course integrate both. So the integral of r dt. Okay, so this is similar to make the integral of k dit divided by I that multiplies k minus I equal integral of r dt. Okay. So we want to break this down. So when we say k divided by I, k minus I, this equals a divided by I plus b divided by k minus I. This equals a times k minus I plus b times I divided by I, k minus I. As a result, we have that for I equal k is a times k minus k plus b times k. So k equals b times k. B is 1. And for I equal 0, k equals a times chi minus 0 plus b times 0. So thus we have k equals a times k, so a is equal 1. So as a result, our equation k divided by I k minus I equals 1 divided by I plus 1 divided by k minus I. So we can continue our equation above. This is just a separation of the variables. Okay. We can continue our separation above by saying, okay, the integral of 1 divided by I plus integral of 1 divided by k minus I equal integral of r dt. But this is the integral of the logarithms, as we have seen above. This is a minus because the I is with minus, equal RT plus a constant. If we exponentiate then we get our final result, I divided by k minus I equal a constant a to RT, being the constant the initial condition of the infected people divided by k minus the initial position of the infected people. So if we put that together, the final equation is k divided by 1 plus k minus I0 divided by I in t equals 0 when e minus exponential RT. Okay, so this is the way the infected people will be distributed over time. Okay, so this equation is the solution. Some people have asked, hey, in the exam, can you ask for practical but also for theoretical things, or only practical problems? In the exam, I can ask anything that we have seen in the lecture. And this is an example, okay? I could ask you to do these calculations and give me the solution of the equation, okay? So the thing is that for R, let's paint this this equation for different values of R. For R bigger than 0, we infect faster than we cure, okay? And as a result, we have following behavior of the system. This is the time. And this is I of t, okay? So the system behaves like this. We have an initial condition, I in t0, and this is k. Okay, this is the asymptotic value that we are going to approach in time. So the system behaves like this. Okay, so we don't kill the infection, it just gets stable. So for R, it could also behave like this. Okay, so depending on the values, but the thing is that asymptotically we go to the value k. So if R equals 0, we infect at the same rate as we cure. Okay, and as a result, our system is again having a constant value. Okay, so if R equals 0 in the equation above, k divided by 1 plus k minus I0 divided by I0, because R is 0. The exponential is 1. Okay, so this is k times I0 divided by I0 plus k minus I0, and then we have this goes with this, k goes with k, so we have I0 constant. Okay, let me paint it with color. So because we infect at the same rate as we cure, we stay constant. And if R is smaller than 0, okay, so if we are infecting, imagine we give condoms away for free in the campus, okay, so we infect slower than we cure, we get following behavior. The infection dies off. Okay. And goes to 0. All right. So, any questions? This has direct implications when you study a system with inventory, or when you study an interaction with a customer, or when you study just this function can be anything that underlies an interaction between elements in a network, IoT networks, whatever. Okay. So, questions, please. questions? No? Okay, then I continue to the two-dimensional problem. Well, one might ask, please give me another example of how to separate these functions for the integration. Let me give you another example. This is sometimes example separation of variables for integration. So imagine I have this function, let's say 7 divided by x minus 2, 3x minus 1, okay? And I want to put it, I want to prepare this equation so that I can integrate it easily with the logarithm and stuff. So what we do is we take the 3 out because we need the x alone. So this is 7 divided by 3 times 1 divided by x minus 2, x minus 1/3. And this is a divided by x minus 2 plus b divided by x minus 1/3. Okay, so this equals a times x minus 1/3 plus b times x minus 2 divided by x minus 2 times x minus 1/3. So 7/3 equals a x minus 1/3 plus b x minus 2. So if x equals 1/3, we get 7/3 equals b times, no, wait, I don't have space there. I'll do it one level below. So if x equals 1/3, 7/3 equals b times 1/3 minus 2. So 7/3 equals b times minus 5 divided by 3. So b is minus 7 divided by 5. And if x equals 2, 7/3 equals a times 2 minus 1/3. So 7/3 equals a times 5 divided by 3. So a is equals 7 divided by 5. So as a result, we can say that 7 divided by x minus 2, 3x minus 1 equals 7 divided by 5 times 1 divided by x minus 2 minus 1 divided by x minus 1/3. Okay? And we can integrate that easily in our system. Okay? So the integral of 7 divided by x minus 2 times 3x minus 1 to x equals the integral 7 divided by 5, or better, equals 7 divided by 5 times integral of 1 divided by x minus 2 minus integral of 1 divided by x minus 1/3. And this is 7 divided by 5 logarithmus of x minus 2 minus logarithmus of x minus 1/3 plus a constant. Okay, so this is basic calculus. I guess this is from the first semester, but in this case necessary to describe the dynamics of the system. Okay. Good. So, any questions? Wait, this one? Yeah. Yeah, so A, you see this is this, and this is equal to this, right? So when I have A is 7 divided by 5, A is multiplying, it's like being here, okay? It's like if I put here on top, A is 7 divided by 5 divided by x minus 2. And when I say B, okay, I put minus 7 divided by 5. So 7 divided by 5 minus times 1, 7 divided by 5 minus, divided by x minus 3, x minus 1/3, okay? This is called separation of terms. It just helps us with the integration. It's a good trick. Yeah, you can try it with different numbers. If you have problems, come back to me and we will have time for exercises in the next lecture. So, but you need to tell me because yeah, you need to tell me that you need it. So or if you want, we can do another example. I don't care. So let's who did ask? Can you put your microphone again? So your name, Nicolas. Okay, Nicolas. Let's do another example together. Okay. So 3 divided by x minus 1, 2x minus 5. Okay. So I ask you to integrate this. This is not integrable, so easy. So we want to separate it. Okay. So let's take the equation x minus 1 to x minus 5. Yeah, the denominator and numerator. So we can do it step by step. So x minus 1, we leave it. Okay. So I take the 2 out of the parentheses. So 2x, but now I need to say 5 divided by 2. Okay? Is that okay? Okay, then we say 3 divided by 2 multiplies x minus 1 and x minus 5 divided by 2. And then I separate it. I say this is equal to a x minus 1 plus b x minus 5 divided by 2. So now we need to know what a and b is. Okay, so this equals a times x minus 5 divided by 2 plus bx minus 1 divided by x minus 1, x minus 5 divided by 2. Good. Then I say 3 divided by 2 equals a times x minus 5 divided by 2 plus b times x minus 1. So now we give numbers, we give values to x. So if x is 1, then 3 divided by 2 equals a times 1 minus 5 divided by 2 plus b times 1 minus 1, which is going to be 0. Okay? That's why we choose x1 to take 1 away. So 3 divided by 2 equals a times minus 3 divided by 2. So a is minus 1. Okay? And if x equals 5 divided by 2, then 3 divided by 2 equals a times 5 divided by 2 minus 5 divided by 2 plus b times 5 divided by 2 minus 1. So 3 divided by 2, this is going to be 0, equals b times 3 divided by 2. So b is going to be 1. And then I take these values and I put them here. Okay? So with this in mind, I'd say 3 divided by x minus 1 to x minus 5 equals minus 1 divided by x minus 1 plus 1 divided by x minus 5 divided by 2. Good. If we want to do the integration, this is minus okay, and this is going to be minus logarithmus of x minus 1 in absolute value plus logarithmus of x minus 5 divided by 2 plus a constant. Okay. Now the 3 disappeared because this equals this. You know, we are taking all the thing into consideration. The 3 is always there. It's always here, but it disappears because here we have a minus 3. Okay. So I don't know. This just I just took random numbers. Okay, I didn't prepare it. I just did it for you now. But this is the way to do it. It's a let's say relatively simple method to integrate these kind of functions. Okay, is more understandable now? Okay, so any more questions? Okay, so we now go on and describe a two-dimensional system. Okay, two-dimensional dynamic system, which is going to be a little bit more tricky. Okay, now we have two functions. And again, we are going to do sex and math, okay? I think it is more fun if just like last week and this example also, it is more fun for young people to learn these things with these examples than with business machines and cash flow and I don't know. So let's talk about sex, okay? We have, or let's talk about love, okay? So we have Romeo, who's has a relationship with Julia, okay? So, and the love of Romeo to Julia is described by the function RT, and the love of Julia for Romeo is described as the function JT. Okay? And Romeo and Julia interact. So the love functions for each other are T and JT depend mutually on each other. So if, I mean, depending on their characters, if sometimes when Julia loves Romeo and he notices that Julia loves him, Romeo will say, no, I'm not interested anymore because she already loves me, so I don't care about her anymore. So, or Romeo stops loving Julia, and in that moment, Julia falls in love with Romeo. Okay, so the interaction between these two characters, two friends, Romeo and Julia, can be described with dynamic systems. Okay, so to describe this interaction, we need 4 parameters. A, okay, describes the intrinsic love of Romeo to Julia. So it does not depend if A is positive. Romeo increases love to Julia independent of Julia. Okay, and if it's negative, Romeo decreases love to Julia independent of Julia's behavior. Okay? So the second parameter describes the influence of Julia on Romeo's love. Okay, so if B is bigger than 0, Romeo loves Julia more if she is charming. If B is more than 0, Romeo loves Julia more. If she rejects him. So some people fall in love with others that are charming. Some people fall in love with others that are assholes. Okay? So as a result, we can say that the dynamics of love for Romeo with time are dependent on A and on B. Depend on the values of A, depending on the values of A and B, we can say that, and this depends on the personality, okay? Some people, as I said, fall in love with others that are nice. Some people fall in love with others that are assholes, okay? So for the other parameters, this is exactly the same for C and D. It's the same, changing the numbers, changing the names, sorry. So we have that the variation of the love for Julia, of Julia to Romeo is equal to C times R plus D times J. So if C is positive, Julia falls in love with Romeo when he is nice. This depends on the psychology of Julia. If C is negative, Julia falls in love with Romeo when Romeo is an asshole. And if D is positive, Julia increases her love for Romeo independently of Julia's behavior. And if D is negative, Julia decreases love to Romeo independent of Julia's behavior. Okay? So these two equations describe the dynamic system. But you see that the first derivative of R depends on R and depends on J, because both are interacting. Okay? And of course, this is just an example, but in any business interaction, whatever your business partner does influence your decisions. Okay? So I am trying to describe this with sex and love. Okay? I guess this is not sex, this is love. But you see that this is universal. Okay, so if we understand this problem, we will understand the business problems as well. Any questions so far on the problem definition? Yeah. Mm-hmm. Yeah, so exactly. So when D is describing the interaction of the love of Julia and the dynamics of the love of Julia, okay? So imagine Julia is in her room alone without interaction with Romeo, and she starts thinking on the boy, okay, oh, he's so good, and she falls in love with him without Romeo doing anything. This is described by D. If D is positive, she's going to fall in love with him. If D is negative, she's going to start hating him without him doing anything. Okay? Does it make sense? Yeah, no, it depends. It can be, yeah, it can be anything. Okay, it just depends on the symbols of the parameters. This is just a general case. Okay. So it depending on the characters. So you can try to inspect your own relationships and try to find out what type of relationship you have, okay, with your boyfriend or girlfriend or whatever, okay? So you can inspect how the dynamics are going to be. In other words, you can foresee the future of your relationship because if you understand, if you are able to describe your relationship with your partner with these coefficients, you will know how your future relation, the future of your relationship will be, depending on the psychology of your partner. So auf Deutsch, ihr könnt vorhersagen, wie eure Beziehung sich entwickeln wird. Und das finde ich ziemlich cool. So, we can describe this in a vectorial notation. So if we say x is a vector of two functions, and we have a matrix A of A, B, C, and D, then we can say that the derivative of x with time is equals A times x of time. Okay, and this is the general equation of the love of Julia and Romeo. Okay, so general equation, general dynamic equation for two variables interacting. You can of course say the two functions are inventory and quality, or you can say this is a problem of customer interaction, price, and customer behavior, or how often they come to the store, whatever. Okay, so this is just an example to make it more attractive to you. Young people are by nature interested in love affairs. So in order to understand the qualitative behavior of the system, we diagonalize our equation by finding the eigenvalues and eigenvectors of the matrix. So the general solution, why we do this? The general solution of the equation is x of t equals r of t j of t is a constant times the first eigenvector times it's a function of time times exponential of the first eigenvalue time plus a second constant times the second eigenvector times the exponential. Okay? So this is the general solution. We can compute the eigenvalues and the eigenvectors because we know how to do it. So we have our matrix A, B, C, and D. So we can say the determinant of A minus lambda I equals 0. This is the determinant of A minus lambda, B, C, D minus lambda equals 0. This is I minus lambda, T minus lambda minus CB equals 0. So as a result, we have lambda square minus lambda A plus D plus AD minus CB equals 0. Okay, so when we perform the Mitternacht-Formel, we have A plus D plus minus A plus D square minus 4 times AD minus CB divided by 2. Okay, so A plus D plus minus A square plus D square minus 2AD plus 4CB divided by 2. Okay. So if this equals lambda A plus D plus minus A minus D square plus 4CB divided by 2. Okay. Remember the meaning of A, B, and C and D, okay? A, B, and C and D mean A is the own love of Romeo. He's alone in his room and he falls in love or not, depending if it's positive or negative. B is the interaction parameter. C is the interaction parameter, okay? So, good. So from here, this is the general equation. From here, depending on the values, we can obtain lambda 1 V1, just like we did in the past, lambda 2 V2, plug it into the equation above, and Um, yeah, obtain the solution. Let's make some examples. So, example number 1. The behavior of Julia does not influence Romeo. This means that B equals 0. The same would be if the behavior is the same case. The behavior of Romeo does not influence Julia, okay? C equals 0 is the same because we get our eigenvalues are A plus D plus minus A minus D square plus 0. You know, this 4CB just disappears. Okay, divided by 2. So this means this is A plus D plus minus A minus D divided by 2. So if we take the plus, we get lambda 1, which is going to be A, first eigenvalue, and the second eigenvalue is going to be D. Okay? So in this case, for the first eigenvalue, we say A V1 equals lambda 1 V1. Let's say we have our equation A is A0, 0, D. V1 is our first component. This is A V11 V12. Okay. For the first eigenvector, we have A V11 equals A V11 and D V12 equals A V12. Okay, so from here we can say that V12 needs to be 0. Okay, so V11 can be let's say 1. Okay, so meaning that the behavior of Romeo and Julia are independent. Our equation turns out to be x of t, a constant, plus the vector 1, 0, to an exponential of at plus a constant plus the vector 0, 1 times dt. Okay, if we represent this, remember this is the functions r and t, so we can say that the behavior, the love of Romeo is going to be a constant AT, and the love of Julia is going to be also a constant DT. Okay? So this is what we called idealized. Maybe you've heard the expression platonic love. They don't interact. If they are in love, let's say A and D are positive, we can represent this in a two phases diagram. If they are in love, then they will be in love, and their love will grow exponentially. Okay, it will grow forever because they don't have any interaction. If they both hate each other, they will hate each other forever, so both are negative. Okay, eternally in love here, and here eternally hate. Okay, so if Julia loves Romeo but Romeo hates Julia, this will increase also. Okay, so Julia will love and suffer forever, and Romeo will hate Julia forever. Love hate, eternal, and the same thing will happen. Eternal love hate in the other way around. If Romeo loves Julia but Julia hates Romeo. Okay, this means that the point 0 is an unstable equilibrium. Whatever happens in the beginning will determine the behavior forever. Okay, so we have just described a situation of platonic love when A and B and 0. Does this make sense? Now let's imagine a more realistic situation. Romeo likes charming Julia and Julia likes asshole Romeo. Okay? So Romeo likes charming Julia and Julia likes asshole Romeo. Okay, so A is going to be let's define the parameters, okay, mathematically. So A is minus 0.5. Romeo does not find Julia attractive. Okay? But B is 1. So if Julia is charming, Romeo falls in love. Of course, you can change the parameter later. It's just a game. I'm just trying to make it fun for you to learn. Okay, just a little game. So C is minus 1. So Julia does not find Romeo attractive. And D is minus 0.5. So Julia rejects Romeo when he shows love. So she likes bad guys, okay? Only when Romeo hates Julia, she falls in love with him, which is an interesting psychology, but it happens. Okay, so what we have here is that our eigenvalues are lambda, are going to be minus 0.5, minus 0.5. Let me draw the equation again. A plus D plus minus A minus D squared plus 4CB divided by 2. All right, so this is cool. We have A plus D is minus 1 plus minus 0 plus C times B is minus 4 divided by 2. All right, so we have here a situation minus 0.5 plus minus I. All right. This means that we have a system that is going to be oscillating, okay? So lambda 1 is going to be minus 0.5 plus I. Lambda 2 is going to be minus 0.5 minus I. Good. Well, let's hit it. We have A V1 equals lambda 1 V1. So A is minus 0.5, 1, minus 1, minus 0.5, V11, V12 equals minus 0.5 plus I, V11, V12. All right. So let's minus 0.5 V11 plus V12 is minus 0.5 plus I V11. Okay, and minus V11 minus 0.5 V12 equals minus 0.5 plus I V12. Good. From the first equation, V12 equals I V11, and from the second equation we get basically the same, okay? But V12 is I V11, which means if V11 is 1, V12 is I. So our first eigenvector is 1 and I. Okay, we can solve the other eigenvector. in a similar way, and the equation, the solution of the equation is going to be like this. Exponential of minus 0.5t, and then a constant a, cosinus of t, sinus of t, plus a constant b, minus sinus of t, cosinus of t. Okay, this is the equation, but what does it look like? How can we explain it? Okay, let's look at it from a qualitative way, and let's explain what happens. This is J. This is this is R. Sorry, but it doesn't matter. This is R of t. This is J of t. Okay, so if Romeo and Julia start here, let's say, finding each other attractive, what will happen is this. They will start like this, and Julia will love Romeo, but Romeo will start not liking and not loving Julia, and then they will turn, and they will hate each other for some time. Then Romeo will start loving Julia again, and Julia will still hate Romeo, and then they will love each other again, and then they will and then Julia will love Romeo, but Romeo will not love Julia, and then they will hate each other again, and so on and so forth, until they cannot bear it, and that the relationship is broken and they break up. Okay? This explains the dynamics of Romeo and Julia's love. Maybe you have experienced a situation like this, in which the characters are not mature. The characters are not mature. They fall in love with someone that treats them wrong. Okay? They think they can change the other guy or the other girl. As a result, we get broken people, okay? Broken relationships, downward spirals. Okay? This happens in business as well. When you get one supplier and you are squeezing the supplier, at some point the relationship between supplier and customer breaks down. All right? So, are we cool? Now you can go ahead and say, okay, I think with my boyfriend or with my girlfriend, I think that my relationship right now can be deemed with different parameters. Let's make another example. Third example. Third example is Romeo is an ice man. Oh no, Julia is an ice woman. So Julia does not feel. She just doesn't feel. And Romeo is like fire, okay? So C equal D equals 0. And A and D are bigger than 0. So lambda is going to be A and B. A plus square root of A square divided by 2. So the first eigenvalue is going to be A. Second eigenvalue is going to be 0, okay? So the equation is going to be x of t is going to be a constant times the first eigenvector EAT plus a constant times the second eigenvector. Okay? Because lambda 2 is 0. So let's calculate the first eigenvector. A is going to be AB 0, 0 times V11, V12 equal A V11, V12, which is going to yield V111, V12, 0. Okay? It's the only solution to this. So our first eigenvector is going to be 1 and 0. Julia does not interact with Romeo. And the second one is actually going to be a degenerate solution. Julia can do whatever she wants. It can be any behavior. Nothing will stop Romeo from loving her. Okay? So it's a degenerate. Can go in any way. So let's say we take 0, 1. As a result, we have following behavior. C1, 1, 0 exponential. C2, 0, 1. Okay. This means that in our phase representation, we have Romeo here, we have Julia here, and Romeo will always increase independently on when we start. Romeo's love will always increase, and Julia's love will remain constant. So if we start there, Romeo's love will increase. If we start here, Romeo's love will increase. If we start here, Romeo's love will increase. If we start here, Romeo's love will increase, independently of what Julia does for him or against him. Okay? Anyway, any questions